First of all, welcome everybody to our webinar session for today, Moon Rocks, How Lunar Samples Connect the Past, Present, and Future. We are broadcasting from the NASA Johnson Space Center in Houston, Texas. I would say sunny Houston, Texas, but it's kind of cloudy outside. We want to welcome all you participants from 17 different states across the nation that have actually registered to participate. Some of them are here live. Some of them will watch the archive. So we welcome all of you. And we do have students that kind of span from grades 3 all the way up through adults. So we're so glad all of you are interested in learning about moon rocks today. One thing I do want to thank is our Lunar and Planetary Institute friends, our partners that are actually hosting this webinar. We're testing this new system. LPI has enabled us to be able to do that. They have some great resources on their website. Feel free to check them out. We'll make sure to include the link to their website so that you can see their resources as well when we do send a follow-up email. Now, I also want to really take a moment to welcome our featured speaker, Juliane Gross. She is our Deputy Apollo Curator here at the NASA Johnson Space Center, and she is a very busy scientist. And we are so lucky to have her with us today for today's webinar. Now, we do have future webinars that we'll be having, probably one on Earth Day, one on Mars, so always feel free to check our webinar event website. But again, for today, we're so glad to have all of you, and especially glad to have Juliane with us. So I'm going to try my best to transition to Juliane's slides. And we're going to have Juliane introduce herself before she actually gets started. So let me get her set. Hopefully I'm going to do this and do it right. And it looks like we are all set. So Juliane, I promise not to steal the mouse too often, though I'm going to steal it real quick from you here. But Juliane, let us know a little about you and take it away.
All right. Well, thank you, everybody, and welcome everybody. Clearly, this is a big crowd from everywhere. So, yeah, I'm from Germany, actually. So if you hear a funny little accent, that's because I'm still trying to learn your language. I was born in Germany. I grew up in Germany, and I went through the German education system. I got my PhD in Germany, and then I came to the United States to do a postdoc with the Lunar and Planetary Institute to transition into planetary science. So before I was an Earth scientist looking at Earth rocks. Now I'm a planetary scientist looking at planetary rocks, so rocks from other planets than Earth. After my postdoc, I went to New York City and worked at the American Museum of Natural History there, and I met, I think 2 weeks ago, I met some people from New Jersey, from the Oceanport school there, to give them a little tour. So that has been a lot of fun. I was a research scientist there for about 3 years, working in the Department for Earth and Planetary Sciences. And then I became a professor for planetary science at the Rutgers University in New Jersey. And right now I'm on leave from there because NASA borrowed me for an extended time period to be the deputy curator for the Apollo sample collection here. So now I relocated to Houston, and I'm enjoying this immensely to work directly into the Lunar Lab. And I'll take you, I took pictures. We're going to talk a little bit about what the Lunar Lab looks on the inside and what we're doing with the lunar samples, Apollo and meteorites. So yeah, that's pretty much about
you can use the mouse or the...
Okay, let me see if I can get this to work. So you can see those 3 images. Let me just wiggle the mouse to make sure that you guys can see. So here's the Galileo moon, here's the Cassini moon. These both were done through telescopes, and then this is a picture that NASA took with one of the spacecrafts. You can see how our view of the moon has evolved over time, not only from images, but also what we know about the moon. So we're going to talk about that today a little bit. And that doesn't work. All right, I'm going to click here. So my very first question to you guys, and so remember to answer those questions in your little chat box. Why should we care about the moon? Why should all of you guys become future lunar scientists? Like, why is it important that we care about the moon? What you got? I'm going to give you a couple of minutes to think about it and to answer, to put your questions in the chat. And I think Paige is going to read your answers so
Yeah.
that I know what you think about it. So
Yeah.
type away.
So yeah, why do we care about the moon? Why should you care about the moon? And so I'm sure many of the groups are thinking out there. Creekview High School says because of future colonies there. Corpus Christi says to help us understand the tides.
Yeah.
Duxbury Senior Center says it's our nearest neighbor in space. It's only 3 days away. Maple Place School says because of gravity. San Benito High School is mentioning the moon and water on Earth are connected. Connecticut High School, they said they think it's cool. The moon affects our planet through tides, illumination, and we could potentially even live there. Durgee Junior High School also mentions the idea of gravity. And Corpus Christi also mentions to help us get to Mars sooner. Now, Benito Juarez Community Academy also says it was essential to the space race and future trips to Mars. Murfreesboro Middle School says so we can live on it because it controls our tides as well. So these groups have learned some things in their school. Now, even Curator Services is saying that past knowledge of rocks that make up the moon. And we're going to hear a lot more about that.
Absolutely.
So
yeah.
what do you think, Juliane?
Yeah, these are all really, really great answers, and you're all right. So from the very early moment when humanity had a conscience and looked up into the sky and we saw the moon, there were a lot of questions that we have as people, but also as scientists, and some of these go all the way back to our solar system of like, or if the moon is here and Earth is here, like how did we come to be? How did the solar system form? How old is the moon? How old is the Earth? What was the precursor, so the material that made our planets? How does this all work with, as you already said, gravity? And all of these things, you would think that maybe we could answer some of these questions by simply looking at rocks from Earth, right? But if we look at our planet right here, you can already see one of the big major problems that we have with our planet. And don't get me wrong, I really like Earth, but you can see a lot of Earth is covered in oceans, you can see clouds, right? So Earth is a very active planet. We have subduction zones where we hear the ocean floors, they get subducted into the interior of Earth where it remelts. We have volcanism where we create from the melt new rocks that get extruded onto the surface. We have rain and wind and snow and ice, and all of these abrade the rocks over time, transport them back. Eventually they land up in the oceans, and then they get subducted back into the interior, they remelt, and this whole process starts again. So Earth is a gigantic recycling machine. And that means if we want to learn something about the early Earth and maybe the early solar system, we can't do that by looking at rocks from Earth because they have been changed over time, over and over again, and they have reset. So we have to find a place where we can look at rocks that haven't changed much since their formation. And that place is the moon, right? It's only 3 days away, as some of you already said, so it's our closest neighboring body. That's great. And the moon hasn't changed much since its formation. There's no rain on the moon, there's no winds or anything on the moon. So everything that happened sort of got frozen in time. So that's why we call the moon a museum of planetary history. By looking at rocks from the moon, we can learn something about the planetary formation, the early history, because all of these things got preserved in those rocks. It's also a space probe and time machine, because everything that happened to the moon most likely also happened to Earth. So material that impacted the moon probably also impacted Earth. So maybe we can learn something about organics or where life came from. We can learn something about the solar system climate, of what type of materials were around during that time. And our sun has been interacting with the surface of the moon for billions of years. And so the surface of the moon represents kind of like an archive of the solar system climate. So if we can learn how to read this archive and see what the solar particles are that have changed the lunar surface, we can even learn something about our sun and how our sun has changed over a long time period. So that's why the moon's really cool and really, really important. So 1969, we went to the moon for the first time with Apollo 11, and 1972 was our last Apollo mission, Apollo 17, and there's a picture here that you can see, and that's really one of my very favorite images. We have really nice cameras at the moment. going around the moon where we can take high resolution images, and you can see in the middle here the Challenger descent stage, and here down here is a zoomed in image. You can see even the 4 legs of the lander. If you look very carefully, you can see the tracks that the lunar rover did, and then those here that are a little bit darker, those are the soil that the astronauts disturbed when they actually walked on the moon. Now, over those time periods, the 6 Apollo missions that successfully landed on the moon, the astronauts collected 382 kilograms of rocks and soil. And soil is what we call all the fine-grained material, kind of like the dirt, right? Here's a really, really big sample. Obviously, that is too big to bring back to Earth, which is unfortunate. You can see here one of the Apollo 17 astronauts in front of it, but they collected a lot of big chunks. And they had the same tools that we have as geologists on Earth. So you can see a rock hammer here. They had grabbers and rakes and sample bags, just like we have on Earth. A lot of these tools were on long sticks, I guess is what you call it, because once you're in these really bulky astronaut suits, it's really hard to bend down, and you don't want to fall by accident because you could cut your suit and then you're kind of in trouble. So we got a lot of these samples back to Earth, and from these samples, when we studied them, we have learned quite a bit. Number one, we know the moon is not made from cheese, even though there are a lot of things that say otherwise. But we know that the moon is a differentiated object, and that means it melted and it turned into layers. So if you have a body that completely melts, all the light material that crystallizes, all the light minerals, they float to the surface, just like a piece of wood would float on the water, and all the heavy minerals, they sink towards the center. And so I'm going to steal the mouse back. We end up with layers, and that's how we know that the lunar crust from these like flotation of pelagic clay. Sorry, I'm going to steal the mouse back for 1 minute. There we go. And so we know this because a lot of the rocks from the crust are very white, and they're made from pelagic clay. So that's a mineral that is white. You can see here one of the Apollo rocks, and you can see how white it is because that's almost fully made out of pelagic clay, 90% of that. But over time, the moon has been bombarded with lots of meteorites and asteroids. So there were lots of impacts. You can sort of see in the night sky, you can see sort of like the fractures of that, the scars. And so when we bombard the moon, the crust gets beaten up. It gets broken into pieces. It gets glued back together. Then it gets broken up again. And so over time, a new rock forms, and that's called a breccia. And you can see all these different types of rocks that are now in this one big rock. And we have breccias on Earth too that works fairly similar, not necessarily through impact, but other processes. So this is an impact breccia rock. And so if we look at all these individual rock pieces here, we can learn something about a really wide area of the moon because impacts distribute rocks over a very large surface. Now, eventually the inside of the moon remelted and then made its way through the cracks into these big impact craters. So the melt filled the impact craters like big lava lakes, and that crystallized to form basalt. Basalt is a black rock, just like Hawaii. You all have seen pictures of Hawaii where, you know, the volcano extrudes melt and that makes a black rock, basalt. We have that on the moon too. And if you look into the night sky, you can see all the big basins, the big impact basins that are filled and crystallized with these basaltic rocks. And that's why they're black. And the crust, the original crust that formed from the flotation, as I showed you, the rock is white. And so most of the surface here looks grayish white because, you know, you start impacting things and mixing things. So tonight, if the sky is clear wherever you are, and you look into the night sky, the dark areas you see, those are the big basins that got filled with these basaltic materials. Now, a lot of these rocks that we brought back are very, very critical for all of lunar science. Everything that we learn in lunar science is based on these rock samples, right? And so here's an Apollo 16 rock, and you can see it's a breccia. You can see all these little pieces of glass glued back together. Now, we can use these to calibrate our instruments. So we have remote sensing instruments that go around the moon, and they shine light onto the surface that then bounces back. And then we can analyze that light, and it will give us an idea of what the moon in general is made from, or what the chemistry is of the surface. But we don't know by just looking at the light. We have to calibrate this. So in a lab, we can shine light on these rocks, and then we can get the light back and then calibrate our instruments with it so we get a correct answer. We can also date these rocks directly. And because we know exactly where on the surface they come from on the moon, we can now put an age date on specific craters. And then we can make a crater calibration that we can then apply to other planetary bodies. So the more craters a body has, the older the body is, obviously, because it had more time to accumulate these big impacts. And if we can age date these correctly and absolute, we then know how old Mars is, for example, or how old some of these icy moons are, for example, Europa. Right? And so this is why these rocks are really important. We can also look at things like density or porosity, how closely packed is one of these samples. And then we can apply this to other missions like the Grail mission on the moon that looked at gravity. So we can see features underneath the surface. But we need to know how porous or how dense these rocks are to interpret these data sets correctly. We can look at the chemistry directly of minerals and isotopes, and then we can learn something about how the moon formed and also how Earth formed. And that's how we came up with the gigantic impact hypothesis, where the Earth and the moon formed at the same time from a gigantic impact event. When we look at the magnetics of these rocks, how magnetic they are, and if they recorded a magnetic field, we can even learn something on the interior of the moon and whether there was a liquid core at some point or not. There was at some point a slight magnetic field, so we do think that was at a liquid core at some point to make a magnetic field, just like Earth did. But it didn't last very long because the moon is fairly small. So just looking at these Apollo samples, we can learn a lot, and a lot of other lunar sciences is directly informed from these rocks, and that's why they're so important to us. Now you can say, well, that's great. We've been there, we've done that. So why should we go back to the moon, right? There's a lot of questions that always come up where people argue, well, should we really go back to the moon? Why don't we directly go to Mars? You know, do we really need new samples? Like, why? So here's my question to you. Why should we go back to the moon? Or should we go back to the moon, right? And remember to put your answers back in the chat box, and then Paige will read them out to us. And I'm curious to see and hear what you think.
Awesome. So let's see what you all have to come up with, because I bet we all have some individual ideas of why we should go back to the moon. So we're really interested to see what you have to say. So Corpus Christi School says so we can learn more about the moon. Presque Isle Middle School says to explore more of it and learn more. Downs Elementary is talking about potentially populating the moon with people. Creekview High School says to further the space program and eventually get to Mars. And occupy Mars. Look at all these answers coming in.
Goodness,
Connecticut High School, they're saying we have better technology and can learn more now than we could 50 years ago. Here's Benito Juarez Community School to better have quality cameras and scientific instruments so we can get better samples and learn more. Murfreesboro Middle School says to discover things we may have missed. Downs Elementary says to explore the dark side or the far side of the moon, because it isn't actually always dark. NAU, our Northern Arizona group, says it's part of NASA's exploration program. And Downs Elementary also adds in, and we haven't gotten everybody, but they also said to experiment to see if people could live there. And I love this from Curator Services just because it would be wicked cool to go back and continue exploring. And even Maple Place School says we have better technology, and that technology really is fantastic. So we've got a lot of pro-moon people, I think, and they've got great ideas.
I love it. These are all really wonderful ideas, and you all had the right idea that maybe we don't know everything about the moon yet, even though maybe we think we do, but do we really, right? So if we go and take a look, so here you can see the moon, and you can see where all the Apollo missions landed. Here's 11, 12, 14, right? So if we overlay the outline of the United States, this is how large the United States is compared to the moon. So the moon is actually fairly small, right? And if I will give you 6 missions, and you land 4 of your missions in the United States and 2 of the missions in Canada, because Canada would be right here, right? And you were going to collect 382 kilograms of rocks. Could you tell me how the North American continent formed, or the entire Earth, right? And the answer is no, because you would miss a lot of cool places. You would miss the deserts, you would miss the Amazonian, you would miss the swamps. You know, there's a lot of cool places on Earth that you would not get rocks from just by selecting these few locations here. So the Apollo missions only sampled a very, very small portion of the lunar surface, right? Now we have better instruments, and I said we have remote sensing spacecraft that go around the moon and make maps of the moon, of how the chemistry looks like. And if we look at these, here's a map of the iron distribution on the moon. And this area here, that's the near side. That's the side we always see. This here is the far side, the side that always faces away from us. Sometimes people call it the dark side, but that's not quite right, because sunlight will eventually also hit that surface. So we call it the far side because it's far away and we never get to see it, right? You can see this is the area where all the Apollo samples come from, right here, where it's really, really high in iron, right? The rest of the moon is not so much high in iron. Now we can look at other elements too. This is titanium, same thing, very, very enriched and really high in the area where the Apollo samples come from, but not the rest of the moon. Here's thorium, a radioactive element, again, very, very high where the Apollo samples come from, but the rest of the moon doesn't have it. So the Apollo samples are geologically extremely interesting because they're very special. They come from this really special area of the moon, but they're not representative for the rest of the moon. So a lot of our models of how the moon might have formed, they might be wrong because they're all based on these Apollo samples. So we do need to go back and collect samples from other areas on the moon. And that's why we should go back, because we need to investigate all the mysteries of the moon, right? We need to learn more, as most of you already said. We can learn more about Earth by looking at this. We can learn more about our solar system climate. And we can see more about what the moon in general is represented by, other features. We have also learned, after we've been there with humans, with our remote sensing instruments and better instruments and technology, we have learned that there are areas on the moon that might have frozen water, right? And if we go back to these places and we can find the water, you know, we could use this water for long-term exploration. We can take the water and break it apart into hydrogen and oxygen. We can maybe turn that into rocket fuel. We can maybe use this to like breathe. We could use it for water for the astronauts if we go back there, right? We also need to learn, or it's a good place to learn how to live and how to operate on another planet. If we ever want to go to Mars, the moon is so much closer, and therefore, you know, if something bad happens, we can get there faster and rescue people quicker. So if we can go there and learn how it is to be on a different planet, how to live there and how to operate there, and talk back to Earth over a longer time period, we can learn a lot about what potentially could go wrong, how we need to evolve our technology better to make this really happen, right? To build a little station here. And so therefore we can improve or prove our technologies that we need before we actually send astronauts to Mars. The moon could potentially become a little base where spacecrafts could come refuel that, you know, with the fuel that we make from the water, and then from there go to Mars. It's so much easier to launch something from the moon because the gravity is so much lower than from Earth. So if we can learn how to operate there and live there and do work there, we can learn a lot about how we need to operate and how we need to communicate and how we need to behave on our way to Mars, right? And that's why NASA decided on the Artemis mission, we're going to go back to the moon. The first woman will be on the moon, which is I'm super excited about this, obviously. We will go to the South Pole, because that's where we think all the frozen water is located. And we will collect samples. We will collect better samples, different samples from Apollo. And then we will analyze them and see what we can learn. And then eventually get from the moon to Mars, which you can see here in the background, right? So NASA had a little bit of foresight that this might happen in the future. So when the Apollo samples were brought back, they decided to keep some of the Apollo samples unopened, you know, still in a pristine stage when they were sealed on the moon, because when they were brought back originally, NASA knew that technology will evolve with time and that we might come up with questions about the moon that we haven't even thought of yet. And so they kept some of these samples pristine. And now is the time, after 50 years of Apollo 11, to open some of these samples. So last year in November, we had the ANGSA program that started, and that stands for Apollo Next Generation Sample Analysis. And that is the bridging between the gap from Apollo, which was the past, right, and Artemis missions, which are going to be our future. And so we are going to analyze these unopened Apollo samples with new technologies and apply everything we've learned so far so that we know how to better collect samples when we go back to the moon with Artemis, so we can really ensure that we get the maximum science out of it, that we know how to keep samples frozen, that we know how to look for the water and all of these stuff. So last year in November, we opened the first of the unopened samples. And I'm going to show you where all these samples are stored now. So the Apollo samples are stored in the Pristine sample vault. This is Ryan, that's the other Apollo sample curator. You can see how thick the door is. Right? I'm using Ryan a little bit as like a scale here. So it's a super thick door that we have to open. It's a safe, right? It's a vault, just like in a bank. So we open this door, and then this is what the inside looks like. And you can see we are all dressed up in these special suits. We call them bunny suits. So these are clean rooms. That means the particles in the clean room are really, really low. There are only a few hundreds of particles per cubic foot. Normally, in normal air, how many particles do you have in normal air? Tens of thousands particles, right? And so in these labs, we're filtering the air so that you only have a few particles per cubic foot. So we cannot wear our normal clothes because that would introduce more particles to the air. So we're all dressed up in these bunny suits. And in these cabinets here, this is where the Apollo samples are stored. Here you can see me explaining this to a different scientist. You can see there are big windows so we can see into the cabinets. These cabinets are filled with nitrogen air. Here you can see us. So these are gloves, and we have little covers on it. When we take them off, you can see how the gloves come out here. So the nitrogen air is under positive pressure, so it presses out. So if one of these cabinets should leak at some point, the nitrogen air just goes out, but no, earth air gets sucked into the cabinet. So that's for protection for the samples. So my questions to you is, and here each cabinet is for a specific mission. So this is AP16. That means these are all the rocks from Apollo 16 that are stored in these containers here. They're all sealed, so nobody can go in and steal them, right? We know who's going to be in there because they have to break the seal if that was possible. And we're not cross-contaminating between missions. So each mission gets their own glove box. So my question to, before I get to my question, obviously, when we want to work with these samples, we have to put our hands in the gloves and then work inside the cabinet. So here you can see me working inside one of these cabinets. These gloves are one size fit all. So if you have small hands like me, and you have massive gloves on, to work inside these glove boxes and handle tools is really complicated because you can't feel much, and you have, it's kind of awkward. And so we have to go through a lot of training in order to do this. All right, so we never touch the samples. So my question to you is why? Why are all these Apollo samples stored in a clean room? Why are they stored in a nitrogen air-filled glove box? Why don't we ever touch them with our bare hands or lick them, right? Don't lick Apollo rocks. Why is this? Why are we doing this? All right, so put your answers in the chat box, and Paige is going to read them again. I'm very excited to hear about your thoughts.
Yeah, so who would have really realized all that goes into actually working with these moon rocks? But now we want to kind of have an idea of what you're thinking. So Connecticut High School saying there are nitrogen-filled air boxes to avoid contamination. Our solar system ambassador from Georgia says to prevent cross-contamination and keep them pristine. Maple Place School says to protect them from weathering. Corpus Christi says so they don't erode. Duxbury is also saying, so there's no chemical contamination from Earth environments. Downs Elementary says, so the samples don't get contaminated with Earth materials. They're listening.
Yeah.
Solar System Ambassador in Florida says to prevent oxidation. NAU says if air gets in, Earth particles will get into the moon rock samples. Murfreesboro Middle School says, again, to prevent contamination. Presque Isle says to keep from being contaminated by germs or even bacteria. No fingerprints on them, Corpus Christi has added.
Yes.
And we don't also want to get our germs on them. Benito Juarez Community Academy is also adding it. So they're definitely listening to you, I think.
Yes, absolutely. You're all right. So we are trying to protect the moon rocks from us. When they were first brought back in Apollo, during the Apollo time, Apollo 11, when those samples came back, people weren't sure whether they're maybe on moon bugs or something, so they were trying to protect us from the moon rocks. Once we learned they're safe, we really have to make an effort to protect the moon rocks from Earth. We don't want to get bacteria on there, so somebody can make a false claim that they found life on the moon, right? We know that's not true. We don't want them to interact with Earth atmosphere because there's a lot of oxygen and water in our atmosphere. And so then if that reacts with the moon rocks, they could rust, they could weather, right? Then we're losing science, right? All like big science questions or ideas. We want to keep these samples pristine, as all of you said. We don't want them to get contaminated with Earth atmosphere or Earth particles or Earth germs and bacteria. So yes, you're all right. That's why we have a very rigorous process of how we get dressed. We get actually air showered before we can go into the lab. We are keeping tabs on how many particles are in the air in the lab. We're even swabbing the place for Earth bacteria to see what is growing, so we can then compare that to the cabinets and the moon rocks and stuff like that. So we're working really, really hard on keeping these samples pristine and as natural as possible. So yes, you're all right.
But that's not a lunar environment in there, correct? That's not like the environment on the moon to just, okay.
No, we can't. Because the environment on the moon is there's no air, right? So that's under vacuum, but we don't have the technology to keep these samples under vacuum at this point, right? And if we want to work on them, we can't really have a vacuum cabinet. You can't really put your hands in there anyways. But this is the next best thing we can do to keep them pristine and safe from us. So in this pristine sample vault, there's a special cabinet that you can see right here. It has a super high technology security measurement. You can see this right here, right? This is what it says: core area must have escort, right? This is where we keep the samples that were sealed on the moon, that are still sealed, that have never been opened. And if we look into the cabinet here, you can see them stored right here. They're still in the containers. So this is a drive tube. When the astronauts were on the moon in Apollo 17, they took a big hollow tube and they drove it into the surface so that you get sort of like a cross section of what the depth of the surface looks like, from surface into depth, right? And they're in Teflon bags and they're sealed. And so there's nitrogen air in the Teflon bags. When they came back, we sealed them. Here is me taking the first sample that was still closed and sealed out. And you can see I'm really excited, but I'm also really nervous because I had to keep it level and I had to walk really slowly so I wouldn't trip over my feet. Because if you trip and you drop it, that's it. We're done. We don't even have to open it because we lost a lot of science. So I was very careful to not mess this up, but the pressure was a little high. And then we have the specially built cabinet. This is the core extrusion cabinet. So if we have a drill core, like the Apollo 17 core sample that we opened in November, we have a special cabinet. You can see the nitrogen air going in. This is the airlock here. Here, the gloves that are all rolled up. And if we look into the cabinet, this is what it looks like on the inside. So this is a core extrusion apparatus. Here is where the moon sample sits, and then we push it out onto this cart, and then we open up the glass top here, and then we have the lunar sample exposed. So this is the first time that we've done since 40-ish years that one of these lunar samples got opened. This is the core team. Here's me, this is Charisse, and this is Andrea. We were the 3 women who actually got to open the unopened Apollo sample. So that was super exciting for us, that now women actively helping and doing the science, and we got to be the first people, the first 3 women to open these Apollo samples. Here you can see us in the process. So on the outside, there was a glass window and people were standing on the outside looking into the room. This is the core room where we were actively working on getting the sample out. You can see me and Cherise here having our hands in the glove box. We're reading off some numbers. We have very special procedures that we need to follow. You can see me here reading off the procedure. We were very concentrated to not make any mistakes. Here, this is on the outside. You can see some of the NASA folks here looking into the core cabinet where we are working right now of extruding the sample. Yes, I look at something very critically. I don't remember what it is. That whole day became sort of like a blur, but we were very, very cautious to not make any mistakes. This is after we had successfully extruded the core. We were very excited and also really exhausted. And you can sort of see this in our faces a little bit. We were like, yay, now we're dead. We're so tired. It was a very, very special day and we had so much fun. This is what it looks like after we had just pushed it out. You can see that the surface looks kind of smooth, and that's because you're pushing it into this glass tube. And so the first millimeter of the core gets mixed, right? This is what it looks like when we take the glass off. And then so we're starting to de-rind the smoothed out surface because that is just a mixed sample. We want to know what sample is underneath that hasn't been mixed, that is very pristine. And so we call this process a de-rinding process. And you can see here, it's the entire sample de-rinded. And here we started the dissection where we now go to plate level and we take every ½ centimeter, we're taking off, we're describing what we're seeing, we're describing the soil particles in there, we're describing different clasts, the textures and the colors. All of this goes into a document that then gets released to the public and other scientists, and then they can request to work and do science on these particular samples. We had to practice a lot, right? Practice, practice, practice. This is one of our practice cores here, where we had lunar simulant and we put simulated class in it, and we practiced how to extrude it and how to dissect it. Why do you guys think that was so important? Why did we have to practice, and how long do you think we had to practice for?
So this is a question for you guys. So think about this. They're opening up a core that had not been opened for 50 years. Why would they need to practice? And like Juliane said, how long do you think they practiced? Why is that important? So let's see what our groups have to say about this. So Duxbury says you only get one shot. Connectquot says the process has to be correct without a second chance. Murfreesboro's mentioned you only get one chance to get it right. Even our solar system ambassador in Georgia says you have to find errors and make changes to the protocol. Maple Place School says practice to make sure you preserve the sample. Curator Services says so you don't screw it up, and maybe you did that for 40 hours of practice. Corpus Christi School is thinking, did you have 3 years to practice? Creekview High School says so you get an idea of what to expect because you only get that one shot. Downs Elementary says practicing to make sure you don't have contamination. Presque Isle is thinking maybe 2 years since you hadn't opened it for over 40 years. Murfreesboro is thinking maybe weeks, maybe months to practice. And NAU is saying, you know, because you don't want to break the real one because it is so old. So, so we've got a range from maybe weeks to months to years to 2 to 3 years. So tell us, Juliane, tell us, and how long this whole process took you.
Yeah, so you all are right. We had to practice a lot because we only get one shot, right? If we do this wrong, we lose science, we might lose the core, we might contaminate it, and then that's it. We can't learn anything new from it, right? So we had to practice a lot. Obviously, we're not waking up one day and then we're experts in this. So there's a lot of practicing going on. So if you're in school and you want to get better at something, right, just keep in mind, you just need to practice. Just like us NASA scientists, we also need to practice to get better at things, right? And so the whole procedure to look at the equipment and actually finding all this old equipment that they used, 50 years ago to extrude these cores, that took 1.5 years to start looking, where are the boxes located? Where are this equipment stored? The actual process of how to extrude the sample, how to, put these things together inside the cabinets, that took us weeks. I think we practiced for about 6 weeks every single day. We had to practice how to put the stuff together while we have these like really awkward gloves on, because you can't really use your fine motor skills as you use normally with your fingers, because now you have these like massive gloves over it. We had to practice of how to communicate with each other, because we are on opposite sides of the glove box. And if you say, hey, can you look at this, or can you hold this? The other person on the other side doesn't necessarily know what this means. So we had to really be practicing how to articulate correctly what we needed or what we wanted, or how to do this, right? And so it took us a long time to practice. And the whole extrusion part, and then the dissecting part of how to very carefully dissect each interval, that took about 6 weeks total. But the whole process started about 1.5 years in the past before we actually extruded the core. So there's a lot of practice going on. So remember, when you guys want to get better at something, right, just keep practicing, because even scientists do that for very rigorous times, because, you know, that way we can get better at something. And for this particular, we only had one shot and we wanted to get it right. So that's why we had a very rigorous practice test. And also we realized some things didn't quite work out very well. And so, as some of you said, we had to reinvent the procedures. We had to update the procedures. We had to write new things in there that nobody ever had thought of. And now that the technology has evolved, we were like, oh, wait a minute. We do this, it's going to be so much easier and less error associated with it. And so we worked really hard to get this done. So here you can see the simulated core. This is the real core, right? These are the simulated class. Here you can see some of the actual lunar class in there. And this is what the core looks like. Here you can see now there's an area that has been dissected a lot more. And you can see there's color variation on the moon. It looks fairly gray, but some of the areas is really, really dark. And so these dark areas that you can see here is because solar wind has been interacting with the lunar surface, and it makes the surface darker than it originally was, right? Underneath the surface, it's still kind of light gray. Okay, well, Artemis is going to happen in 2024, and we will try to learn as much as we can from opening these Apollo samples, these old Apollo samples now, to understand how we can better collect samples in the future. But in the meantime, as we know that Apollo rocks are not representative, if we want to learn something else about the moon that is more representative, we need to get samples that come from areas that are not from here, not from where the Apollo samples were collected, right? And we would have to wait until 2024 to get samples from these areas here. We don't want to wait that long. In the meantime, scientists had found other samples that they can look at, right? We need different samples that come from other areas, random places on the moon. And the only way for us to do this, short of going back to the moon, is to look at lunar meteorites, right? What are meteorites? Meteorites are pieces from the surface that got blasted off the moon through a big impact event, where rocks got blasted into space. These rocks traveled through space and then eventually got captured by Earth's gravity. And then they fell through onto Earth. They made it through the atmosphere. When they go through the atmosphere, it gets really, really hot from the friction. They start melting. And then they eventually land on the surface, and that's when we can go and pick them up. Now, if you look at Earth, right, here's a nice picture that NASA took from Earth. My question to you all is, where on Earth do meteorites fall, right? Remember to put in your answers in the chat box, and then Paige will see this. We're almost at the end anyways. And so I'm just curious to see where you think they fall.
So we'll get a few answers here and see where they fall. So Maple Place and Solar System Ambassador from Georgia and Duxbury and Durgee and Downs Middle Elementary, they're all saying everywhere. Now Corpus Christi School does call out Antarctica.
Right.
I see also Alaska from Corpus Christi School. And Preview's also saying everywhere all the time, as well as NAU as well. So do they really fall everywhere?
Yep, they're right. That meteorites fall everywhere, every day, randomly distributed all over Earth, right? Again, the problem with our planet, when you look at the picture here, you can see that most of the meteorites will fall into the ocean because simply our planet is covered 73% in water. So 73% of the meteorites are lost to science because they are somewhere sitting at the bottom of the ocean. If they fall somewhere, let's say in New York City or in New Jersey or in Alaska or in Houston, but nobody sees them fall, right? They will fall into a forest or a field, and then they just sit there and then rain falls on it, maybe a cow steps on it or cars drive over it. There's wind and rain, so these rocks then weather away, they turn into soil, they got incorporated into earth. So then we lose them again for science, and we can't really find them. They're not pristine anymore. So our best bet to find meteorites are in deserts where there's not much weathering going on, so that they keep they stay pristine. And we have two types of deserts on Earth. We have hot deserts and cold deserts. And Antarctica is a cold desert. It's actually the driest place on Earth, even though it's covered in ice and snow. So here is a view what Earth would look like if you have the South Pole in the center, right? And every year NASA and Case Western University, they send 8 people to Antarctica to go onto the ice plateau right here in the middle of nowhere where nothing is alive, to collect and recover meteorites. And this is Antarctica as a continent, so we will remove all the ice. You can see there are mountains underneath here. So if a meteorite falls onto the ice, it gets frozen into the ice sheet, and therefore it gets protected from weathering. And then the ice very slowly moves, right? It flows. It flows from the center or the top of the plateau all the way towards the coast. And if it encounters a mountain or something, it tries to flow around it, but it sort of gets stalls here where it goes against the mountain. And because the air is so very dry, it ablates the ice away, and all the meteorites that were frozen in the ice shield eventually rise to the surface. And then you just have to go and collect them. And so there's the ANGSA program, the Antarctic Search for Meteorites that NASA and Case Western run. And so here's a picture of that mission from the airplane. You can see how the ice is flowing around the mountains. So these areas here would be good to look for meteorites. Obviously, there will also be rocks from Earth, from these mountains, so you have to get trained on how to spot them correctly. I was lucky to be selected to be one of these people who got to go to Antarctica in 2017 and 18. And these are pictures from my mission. We were just dropped off here by these little tiny airplanes on the ice plateau. And then for 200 and plus miles, there's nothing around there that is alive. Not even bacteria, nothing. And they just drop you there. And then you live in these teeny tiny tents where 2 people can sleep in. And you just go and work there every day for like 6 to 8 weeks and collect meteorites. It's really cold. This was a very nice day. Let me show you a video of a day that is not so nice. Let me see if this works. There you go. These are some of the katabatic winds that go. They're driven by gravity, not by weather. And they just howl, and they make the weather really cold. So the temperatures went to like minus 40 to minus 60 Fahrenheit. So it was really cold. And those are the days that are too dangerous for us to go out and collect meteorites. On average, the temperature was about minus 20 to minus 30. So it's still really cold. The tents themselves are also very cold. So you never get warm. You're just cold. But you have special gear, so you don't die. This is me all bundled up in all 8 layers of my clothing. This is what it looks like when you find a meteorite on the ice. It's right there. We give it a number. We have tongues to pick it up. Here's a close-up image of one of the meteorites, and you can see they're black. That's because the outside melts when it goes through the atmosphere. It's something we call fusion crust. We pick them up. Sometimes the rocks are mixed in with earth rocks. You can see some of the ice peeking through here. All of these are earth rocks from the mountains that are surrounding the area. The one in the center here, that's meteorite. You can see the black fusion crust. And here you can see how it got broken open when it impacted the ice. So we can see that the interior is slightly different. We pick it up with tongs. Again, we never touch those because we don't want to contaminate them with bacteria from us, right? We put them in bags, and then they get shipped frozen back to NASA JC, where we are here in Houston, in the frozen state, and then they get slightly, very carefully unfrozen, and we can start analyzing them and see where they came from. So we have in our collection, in the world collection, about 400 lunar meteorites. The world collection is about 60,000 meteorites, and only 400 of those are from the moon. And because they come from random areas on the moon, we can now learn a lot more about how the moon formed and other common processes on the moon that we didn't know existed based on the Apollo samples. So what we do is we cut these meteorites. This is not a meteorite. This is just an example of what we do. We cut the rocks. we glue them on a glass slide, and then we make them thinner than a human hair. Right? And here you can see a rock that is thinner than a human hair. And we do this because we can now put them on a microscope. We can shine light through, so we can look at a texture. And this is what it looks like when you look under a microscope and see a lunar meteorite. You can see different crystals. You can see the texture. We have special filters that bring out different colors. So if we turn the filter on, we now can distinguish between different minerals. And that will give us an idea of where the rock formed, whether it was a depth, like the lunar mantle, or whether it was a volcano that made a basalt that extruded it onto the surface. We also have a CT scanner. This is not the one that I wanted. This is the one I wanted. So just like we can scan people in a computer tomography where we look at bones or your brain or something, we can do the same thing with rocks. And so we are scanning a lot of the meteorites and a lot of the Apollo samples. This is a little video. So we get a three-dimensional object. So here you can see a fairly small class that we scanned. And you can see all the bright bits. These are very enriched in iron. And so when we slice through the rock now, you can see different pieces of minerals in class. So this is a breccia, but you can see all those white speckles here. That's iron. So this is leftover meteorites, iron meteorites that have bombarded the moon, and that got incorporated into the moon rocks. So if we analyze these leftover materials from these iron meteorites that not only impacted the moon, but most likely also impacted Earth, we can learn a lot about the solar system climate and what type of material was brought to Earth at some point. We can also learn about processes that we haven't seen from the Apollo collection. We have found a meteorite that I'm working on right now. It's a basalt, so it came from a volcano, but it's really young. So we thought the moon was inactive a long time ago, and then stopped being active. But now with these new lunar meteorites, we know that the moon was active a lot longer than we thought. So that is something very new that we need to readjust our ideas about how the moon formed and why it was active for so long. So looking at these rocks, we learned that there's so much more diversity on the moon than was represented by the Apollo collection. That it is why it's so important for us to go back to the moon, to learn how to collect samples correctly, to learn about other processes that we didn't even realize existed on the moon, right? And so this is sort of the end of the presentation. And the one thing that I really want you to remember from this is that the geology on the moon is very, very complex. And there's a lot of things that we haven't discovered yet. And so we need to go back to the moon. We need to study more lunar samples. And that means Apollo, that means Artemis, but it also means meteorites. So you all should become planetary scientists. You should all finish school, come work at Rutgers and get your degree in planetary science and become lunar scientists so that you can help us solve the mysteries of the moon, learn about more of the moon, and maybe you guys will even go as Artemis astronauts and go collect these samples yourselves. I would be very excited if you bring me back more moon rocks. So with that, I would like to thank you for your attention. And if you have any other questions, feel free to put them in your chat box, and I will try to answer them as best as I can.
That is so awesome. Well, first of all, we do have about 6 minutes or so. I'm actually going to stop sharing so we can see you.
Oh, okay.
And so we want to see if you all have any questions. First of all, thank you so much for sharing. All of you can tell she actually loves what she does.
I love what I do.
And there is so much work that does happen and that goes into all that she's working on. And so we actually want to be able to answer as many questions as we can. And you might, if you do have some time, Juliane has said that she's willing to stay on the line for an extra 15 minutes or so. Mm-hmm. So I do see one question that's come in here right off the bat about, with the ongoing concerns with this coronavirus, has that or will that impact your work at all? That'll be our first question.
It probably eventually will. If this particular NASA center will shut down, then we will work from home. A lot of our work is in labs, so we can't really take the labs home with us, obviously. So then we can't dissect the core anymore. We have to wait. Honestly, being in the lab is probably the safest place to be because we're filtering out all these particles, and the virus is bigger, and it's a big particle, so none of these viruses can go into the lab. So if we all lock ourselves into the labs, we will be all safe. It will probably impact our work a little bit, hopefully not too much, but we try to stay as safe as possible. We also try not to contribute to spreading the virus. That's one of the other reasons why if we work from home, we should all stay home and work from home, because there is this population that is at higher risk than some of us, right? And we want to make sure everybody is safe, not just us. So there will most likely be a little bit of impact, hopefully not too much.
And NASA is really big on safety, and we're also really big on science, and that's what we do here in terms of, you know, continuing to do our work as best as possible. Yeah. So great question. So here's one from Curator Services. They're wondering, you know, you mentioned about schooling. Mm-hmm. How many years of school did you need to do what you do today?
Oh, okay. So where the German school system is slightly different. So I went to elementary school and then high school, and then, you know, got my high school degree, and then I went to university. And I got my master's degree. That's the first degree you get when you go to university in Germany. I know here is slightly different, where you get a bachelor's first and then a master's. But that takes about, I want to say it's like 4 years for your bachelor's and another 2 years, so 6 years until you get your master's. And then I went to doctorate school, so I got a PhD, and that took another 3 years. And then that's it. Once you have a PhD, you're good to go. So it takes about, 9 years total from entering university all the way until you get your PhD. And that's fairly typical. Sometimes it takes a little bit longer depending on what your project is. But yeah. And I loved it. It's great. I love learning. I love, you know, I still continue to learn all these new things. I still read a lot of papers and books and stuff like that. So really, the school process never ends for me. I still feel like I'm learning, and I continue to educate myself, you know, and maybe other people. But yeah.
And that's going that PhD route. There are folks that work in our lab that may only have a master's degree or may only have a bachelor's degree. Absolutely. It depends on the work that they're doing and what it is that, like Juliane said, what their project might be. So there is a variety, the sort of cream of the crop that rises up, and you then have to publish all your work. Yeah. It's part of your getting that PhD, but there are certainly different sort of varieties and numbers of years that you can do to be able to work here at NASA and in the lab.
Absolutely.
Now, I just want to be sensitive to the fact that it is the top of the hour, or 2 minutes to the top of the hour. So for those of you that do need to depart and go on to your next class, thank you so much for joining us. We are going to stay on the line to be able to get to as many questions as you can, but again, we are sensitive to your time frames, and Juliane had so much to be able to share, and I'm glad we didn't miss a thing. But if you do have to depart, again, thank you for taking time out of your day to be able to join us and learn from us. And I'm sure we learned a little bit too about what their thoughts are on the moon.
Absolutely. Yeah.
So thank you again. For those of you that want to stay on the line, stick around, because we'll see how long we can keep Juliane here with us.
That's right.
All right. So here's a question from Duxbury Senior Center. They're wondering, how accurate do you think you are with finding the actual location of the moon with the meteorites?
Okay, yeah, so that actually is the holy grail of lunar meteorite science. We don't know, unfortunately, where on the moon these meteorites come from. If we knew, we could then age date the meteorites, and we could put a new date to one of those craters, the source craters where they came from, but we have not been able to do that yet. We need a little bit of better instrumentations, but things are still continuing to develop. We need better remote sensing. We need to be able to calibrate our remote sensing data better, so we need to have more lunar samples to do this with. Right now, we have an idea where certain meteorites come from. We can tell whether they come from the area where the Apollo samples came from, or whether they come from maybe the far side of the moon, like an area that's very different. We have started to learn a little bit more how to pinpoint it a little bit better, but usually we can only say like a vague area where they're coming from. We haven't been able to pinpoint the source crater yet. That is the holy grail, and we're working really hard on doing that, but we haven't been able to do that yet. So that's still something to come, hopefully in the next decades or so. Yeah.
Awesome, and the learning never ends.
The learning never ends.
Absolutely. So Murfreesboro Middle School in Illinois, they're wondering, I don't know if you can picture this, but they saw a small door.
Yes.
What was that small door that you could see within the Pristine sample hall?
The really little door on the wall. That is just in case somebody will ever get trapped inside the vault, right? If somebody by accident closes the door and locks the vault, you're trapped on the inside and you can't come out. That little door, this is like an escape, and so you can get out through that little door into a different room, and then you can call for help and somebody comes in and gets you out. And so that's just a safety measure, because we don't want by accident somebody to be trapped in there and then, die.
Well, and that was a very good observation, Murfreesboro Middle School.
Absolutely.
So really good observation.
Yeah.
Now, Presque Isle Middle School in Maine, they wondered how many samples from the moon have you analyzed personally?
Oh, like numbers of samples? Let's see. Oh, I've analyzed a lot of lunar meteorites. And I've analyzed a couple Apollo samples. So I want to say maybe 15, 20, something like that. Yeah, there's a lot more out there, obviously. But I've been able to personally analyze a small portion of that. My PhD students are analyzing some of these rocks as well. And so it's always really fun to look at new lunar meteorites are found in Antarctica or in other deserts, and like looking at some of the Apollo samples. It's a lot of fun, and I love doing this. I like discovering new things or looking at rocks that nobody has ever seen, and they're really, really old. They're like 4 billion years old or 3 billion years, depending on what sample you're looking at. And it puts things into perspective, right? Like, they're really old. Like, just thinking about what these rocks have recorded, it's very humbling. I love doing this, yeah.
And you say you studied like 15 different rocks. Did you just like come over, grab the rocks with your tongues, never with your hands, and then bring them over to research? Or is there a process people have to go through?
Yeah, there is usually a process. It depends on where the samples come from. So if you want to have an Apollo sample, there's a process. You have to come up with a scientific hypothesis. You have to write a little proposal. You have to submit it to CAPTEM. That's the Curation Analysis Planning Team for Extraterrestrial Materials. That's a group of people who meet twice a year, and they look over all these proposals and requests to make sure that they're sound, and that's a good idea, right? If you say like, oh, I want to have an Apollo sample to make sure, put it in orange juice because I want to see what it tastes like, that's not a good use of an Apollo sample. And so then these people will say, no, your request is denied. But if you have a good scientific idea, a good scientific question, you want to test a hypothesis that will help us to further our knowledge about the moon, then you can get an Apollo sample. Any scientist on this world, no matter where they're from, no matter what country they're in, they can request an Apollo sample. And if they have a good idea and it will help us further our knowledge of the moon and better understand lunar formation and maybe even Earth formation, then these people will get samples. So I had to go through the same process. I had to request samples like this. If you want to have lunar meteorites, they were found in Antarctica because it's a NASA mission. The NASA is curating those, and the Smithsonian is too. You go through the same process. You write a proposal to ask for these meteorites, and then they will send them to you. If they come from other deserts like Northwest Africa or other hot deserts, you might have to buy them for your research. They're very expensive. We don't necessarily have a lot of money for research, so sometimes we can't get them because there are always these private people who think that it would be really cool to own a meteorite or lunar meteorite, and then they're off the market and we can't do research on them anymore. But yeah, there are different ways of getting meteorites. Sometimes it involves money, and sometimes it involves writing proposals.
Awesome. Now, Durgee High School, Junior High School, actually had asked how many pounds of moon rocks were there, and can you tell us in pounds and kilograms?
Jesus, I can't.
And I can maybe help you.
Yeah, I can quickly translate.
So how many kilograms?
So we have 382 kilograms of Apollo rocks,
which is about 842 pounds, I believe.
There we go. Yep. I don't do pounds. We do metric systems in Germany, so and scientists do. As for meteorites, lunar meteorites, I actually don't know what the entire mass of lunar meteorites are, but it's probably maybe 50 to 100 kilograms, something like that, which is like, what, 200, 300 pounds?
And there have only been about 150 or so lunar meteorites that have been collected?
Yeah, so there are 150 stones. Sometimes when a stone enters the atmosphere, it breaks up into 5 or 6 or more stones. And so then they get counted as individual little samples. So we have about 400 total samples, but they come from about 150 stones that just broke up in the atmosphere. So it's not very much. It's probably less than 100 kilograms now that I think about it. Sometimes these meteorites just weigh 15 grams or something like that. So they're very, very precious. Very precious.
So Benito Juarez Community School, there's a student there that says that they really want to be an astronautical engineer at JPL, but they also love planetary science. And they're not quite sure. How do you decide to explore what you want to do?
Yeah, that's a really good question. And my answer is that you don't have to decide right now, right? You can maybe get an internship and try out projects in planetary science or projects in engineering and planetary engineering, and then see what you like about it. When you go to college, you can try out different areas, go to different lectures, see if you can get a research internship or position in a lab at that university, or maybe, we have internships at the Lunar and Planetary Institute here in Houston and at NASA, where undergraduate students can apply, and then they come and work with the scientists one-on-one. So then you get a better idea of like what your interests really are, what you're very excited about. My biggest advice, I think, is like whatever you are most excited about is probably something that you will be really, really good at just because you're so excited about it. And then you can take that excitement and bring it forward to other people and excite them as well. So don't let anybody tell you what you want to do or what you should do. Follow your heart and follow your excitement, and then go with that, because then you will be good at it. And if you're not quite sure what you like best, try out different ways, try out different projects, and then go with that.
And that's great advice. And undergraduate and graduate internships are one thing, but the Texas Space Grant here at the University of Texas at Austin, they actually even have high school internship programs. So if you're a sophomore, junior, or senior, you can look at the SEES, SEES, and we'll send that out in our follow-up email about high school internships to really get that experience, because experience is really awesome to have. So Murfreesboro Middle School is asking, were early NASA scientists worried at all about lunar samples being dangerous to humans? And are they dangerous?
Yeah, so they were worried about that. So they put the samples in quarantine to make sure that they didn't contain anything that could be harmful for us. They don't contain any space bugs or any moon bugs or anything that would be dangerous to us. Now, if we would take the samples and let's say you have lunar soil and you breathe it in, that could be potentially dangerous because the dust is very sharp. It has very sharp edges because it doesn't get abraded into round things like on Earth. And so if that enters your lungs, it can potentially cut your lungs. And there might be some reactions that are not very good for humans in that sense. But we're not breathing in the lunar samples because then we can't do any science on it anymore. So we're not concerned about that. There's nothing in there that could affect us, or viruses or anything. Nothing like that is on the moon or anything. So now we are more concerned about keeping the lunar samples safe from us, so that we don't by accident alter the samples or contaminate them. That's more of a concern right now.
Awesome. Well, a couple of questions had come in while you were talking about the practice samples, and I know Murfreesboro asked about it as well as some others. How close was that practice sample to the real sample that you opened up for ANGSA?
It was as close as we can get it. So this lunar simulant is very fine grained. It's kind of static. It's a little bit more static than the moon. It's not quite the same thing because we can't simulate these lunar rocks very well. But we can try as best as we can so that we have the same grain size we're expecting based on samples that we have opened before. And so we can shove all the stuff into these core tubes and press them in really hard so that we can simulate as best as we can. It's never like the real thing, but it's more about practicing the movements or practicing about what if something goes wrong? How do we communicate with each other to make sure we can come up with plans on the spot to fix it? Or how do we communicate of like, if I need another instrument or another spatula or another, little disc or something like that, how do I articulate this correctly so I'm not by accident dropping the sample or, contaminating the sample that way. So it was a lot about the movements, and then see how it behaves, even though the real core, the real lunar sample behaved very differently than our practice core. But we tried as best as we can.
Awesome. And practice does make perfect, right?
Practice, or as close to perfect as you can get.
Exactly. So now Duxbury Senior Center is asking, so when a scientist asks for an Apollo sample, how big is the sample that they get? Or maybe I should say how big or small is the sample that they get?
So that depends on what you want to do. If you want to make a thin section and look under a microscope, you get something that's about 1 inch round. That's thinner than a hair, so it's not a lot of sample. If you want to get wet chemistry or isotopes done, you need to have a little bit of bigger sample than you are requesting a chip, and that could be 200 milligrams. It could be 2 grams. It depends. So we want to make sure that the Apollo samples, we don't deplete the samples, right? Because in 50 years from now, there might be new technologies and new lunar scientists that come with new ideas. We want to make sure that there's still enough samples for them to analyze it. So we have a pristinity index, and that means when the samples came back, the pristinity index was 100%, because of 100% of the sample is still intact and pristine. We never want to go below 50% of that. So we still have most of the lunar samples, the Apollo samples, above 50%, because we want to make sure that they're preserved for the future, for you guys. When you guys decide to become lunar scientists, that there is still enough sample left over so you can do experiments on them, or you can do science on them. And so usually we give out samples that are fairly small. Sometimes they're a couple of grams, sometimes they're a couple of milligrams. Sometimes it's only 2 or 3 grains, depending on what you need it for.
And for those of you that have maybe checked out the lunar and meteorite sample discs, some of those samples may seem small, but that's in some cases what a scientist gets to be able to study.
Yeah, sometimes they get a lot smaller things.
Yeah, yeah, excellent question and great answer, of course.
Yeah.
So that makes me think of this question from Corpus Christi School that they're asking, so what made you want to be a lunar scientist?
That's a really good question. So I think I was always really interested in how things work in general. I was always interested in how Earth works. And so I became an Earth scientist. I looked at mountains and mountain ranges and subduction zones and fluids and how minerals behave in these. And then I always, as a kid, wanted to become either a farmer or an astronaut. And so becoming a planetary scientist is sort of like the best next thing, because I get motion sick. And so I was like, well, becoming an astronaut and dealing with motion sickness might not be the best combination. But working with rocks from space is sort of the next best thing, because then I still get to explore other planets. I still get to explore other surfaces. I explore them on Earth, but I look at these samples that come from different planets, from Mars or from Moon or from other asteroids that we haven't been to yet. They're really, really old, and it's almost like I'm in space, and it's almost like I'm, on a starship or something, and actually going there. I would love to go there as an astronaut. It's probably not going to happen, because I don't want to vomit when the spacecraft goes up or something like that. But I do enjoy learning. I like learning new things. I like exploring things. And working on the moon gives me the chance to do all of this. My passion to learn new things, to explore other planetary bodies, and that's why I like it so much.
And so it's kind of like, if you've ever heard that saying, if you love what you do, you never work a day in your life.
That's right.
And I feel like you kind of embody that you obviously seem, and maybe you all can see that as well, that Juliane loves what she does.
I love what I do.
Yeah. So that's a great blessing to be able to have.
Yes.
So Murfreesboro Middle School and even our solar system ambassador from Georgia were wondering, what was your favorite thing about being in Antarctica, and can you kind of describe a day in Antarctica?
Yeah. The first thing is really, really cold. I already said this. What I really liked about Antarctica is that it was so magical. So you're in a place that nobody has ever set foot to. So you're the very, very first person to explore this ice shield or ice field. And so I felt like a real true explorer. It's very addicting to find a meteorite that sits on the ice that you know has been in space, or was created billions of years ago, and you get to be the first person who discovers it and recovers it. I love that. It's very hard work because your body constantly needs to keep you warm, so your body is working a lot, even though you don't necessarily realize that. That was hard, but I like camping, so it was basically a big camping trip, just a really cold camping trip. I liked the people that I went there with. My tent mate was amazing. We had a lot of fun, trying to keep each other company, and there were a lot of joking going on. It was a very respectful atmosphere, very safe atmosphere. We had a mountaineer who kept us safe, so that we wouldn't, freeze and die or fall into crevasses and die or something like that. And so that was very nice to have somebody to rely on to keep you safe. So a normal day goes like you wake up, you crawl out of your sleeping bag, and it's very cold, and so you start getting dressed. And I had on eight different layers. It takes about 20 minutes to get dressed. Then you turn on your little camping stove. You have to get ice and hack the ice and then melt the ice and snow to make water. And with that liquid water, you can then make breakfast. You eat breakfast, and then you crawl out of your little tent. You go on ski-doos, and then you go out onto the ice plateau, and then you search the ice plateau for about 8 to 9 hours and recover all the meteorites that you can find. You write down field notes. You try not to touch them or no strip on them or anything, right? There's a lot of things that you have to take into account. Then you drive back to your camp. You have to fuel your ski-doo, so that you might have seen the big red fuel canister cans that were sitting out on the ice. That's how we manually pump and refuel the ski-doos. Then you have to grab your bucket. You have to go hack the ice and fill the bucket with ice pieces so that you can crawl into your tent, melt the ice to make water, because you have to drink a lot because it's so dry there. Then you have to turn on a little camping stove. You have to make dinner. Your food, everything is frozen and sitting on the outside on the ice. So you have to bring it in. You have to cook something. You have to eat. And then you go and meet in a science tent. It's the same small tent. There's nothing in there. So all people cram in there, all the 8 people cram in there. And then we talk about the day, how everybody feels, whether somebody's really cold or not feeling well or is homesick, or everybody, everybody's really happy. I was always very excited and never wanted to leave there because it's such a magical place. It's so beautiful, that there are big ice crystals that you can see, and you can see sun halos, you can see rainbow clouds because there are ice crystals in the clouds. They reflect the light into rainbows, and so there are all these like magical things that happen there, and I just love being there. So you talk about your day, then you go back to your little tent, you write down a blog or write in your diary, and then you have about 6 to 7 hours. And you want to make sure you sleep those hours. So then you crawl into your sleeping bag. The problem is the sun is up 24 hours a day. The tents are yellow on the inside. So you have to crawl into your sleeping bag, take on a hat and put it over your eyes so that it's dark. And then you need to try to sleep, but it's kind of cold. So sometimes it's hard to sleep. And then you start again the next day. And you do this every single day. So you don't get a day off. Unless the weather is so dangerous and so bad that it's not safe to go outside of the tent. And so you do this for 6 to 8 weeks. And so it can become very taxing sometimes, or very tiring. But I loved every minute of it. And I would go back in a heartbeat. I applied again to go back, and hopefully maybe next year or the year after I get to go back. I would love that. It's a very, very magical and pristine place. And we need to make sure we keep Antarctica this way, right? It's a place where any country can come and do peaceful science. So it's not open for exploration or exploitation, but it's open for peaceful scientific studies. And we want to keep it that way because it's a truly magical place. So I hope you all get to go at some point and experience it.
Awesome. And it would be fun to think about some of these students in these classrooms these days, whether they're listening to the archive or participating live, to hear that one of them sometime in the future might go to Antarctica and look for meteorites as well. Who knows? Maybe they'll be there. Maybe they'll be there at the same time as you.
Yes, that'd be great.
Well, with that, it is about 20 minutes past the top of the hour. I think we have gotten through just about all the questions, if not all of them. We appreciate your thoughtfulness in the questions that you have asked, as well as the answers that you provided to Juliane when she asked her questions
Yes.
as well.
Thank you very much. It was great talking to you all and having you here.
Yeah, I told Juliane, you know, there could be like 500 students on the line. Could you feel that there was like 500 there? No. But we're so glad that all of you out there, again, whether you listen to the archive or were participating live, we hope that you have learned a lot, that some of the enthusiasm from Juliane has maybe come through the screen and joined you wherever you may be. And with that, thank you so much for your time and for sharing your expertise with everyone.
Absolutely.
And for all of you out there, thank you for taking time out of your day to join us today. We look forward to connecting with you in the future. We hope we've inspired some of you to want to pursue science as a future career. And any last thoughts for these groups?
Y'all should become lunar scientists.
Lunar scientists, lunar scientists. Hopefully we'll get a few.
Exactly. Thank you so much, guys.
All righty. Thanks for joining us. Have a great day.
Bye.